Ever wondered what a log function is? A log function is an inverse function of exponential functions. So just like addition undoes subtraction, or multiplication undoes division, logs undo exponents, and exponents undo logs whenever you need to go back and forth between the two. How a log is read, if I have something like this would say log base 4 of 16 equals 2, or is 2. And all logs can be written as an exponential equation, and all exponential equations can be written as a log equation instead also. So as an exponential equation, what this would say, log base 4, that means the base would be 4, of 16 equals 2. Logs always equal the exponent. So that means 2 is the exponent. So 4 to the second power equals 16. That's how you rewrite a log as an exponential equation. Likewise, we can go the other way. If I said 5 to the third power is 125, if I rewrite that as a log, we would say log base 5 of 125 equals 3. Remember, logs always equal the exponent. So let's do some more practice with that. Let's just practice going back and forth between the two. So we're going to rewrite each one of these in exponential form. So log base 2, that means 2 is the base. Logs equal the exponent, so 4 is the exponent. 2 to the fourth power equals 16. So this next one, log base 4, exponent 0 equals 1. 4 to the 0 power equals 1. The next one, 12 to the first power equals 12. And the last one, 1/4 to the negative first power equals 4. So right now we're just practicing going from log form to exponential form. Now let's practice going the opposite direction. This first example would be log base 5 of 25 equals 2. The next one, log base 10 of 0.1 equals -1. The next one would say log base 8 of 4 equals 2/3. And the last one, log base 6 of 1 over 216 equals -3. So now that we know how to go back and forth between them, let's use that to evaluate some logs. So if I want to know what log base 4 of 64 equals, what I'm really trying to find is what exponent of 4 gives me an answer of 64. We know that 4 to the third power is 64, so log base 4 of 64 is 3. That's my answer. Another example, my base is 5. I want to know what exponent gives me an answer of 0.2. This one's a little trickier. It might be helpful to write 0.2 as a fraction instead. 0.2 is 1/5. 5 to the negative first power is 1/5. So that means that answer is -1. Next one, 1/5 is the base. We don't know the exponent, but we want an answer of 125. Here's another trickier one. We know 5 to the third power is 125. That means that 1/5 to the negative third power is 125. So this is -3. And the last one, the base is 36, and we want to know what exponent gives us an answer of 6. Well, the square root of 36 is 6. And another way of saying the square root is raising 36 to the 1/2 power. So this answer is 1/2. Two special types of logs that you can find on your calculator are the common logs and the natural logs. A common log means if you write log without any base, there's an invisible 10 there. And natural logs are logs that have a base of e. We write those as ln of x. So how this applies is if you have log of 8, like this first example, there's no base there. And because there's no base written there, that means the same thing as log base 10 of 8. Or in other words, 10 to what power equals 8? Well, we don't know what exponent of 10 equals 8. That's not a rational number. Luckily, there is a log button on your calculator. So for the common log, you can just type in log 8 on your calculator to get an answer of about 0.903. We'll do 3 decimals on these. So another example, this one of a natural log of 19. Natural log is the same thing as saying log base e of 19. Or in other words, e to what power equals 19? Well, this is tough because e is an irrational number as it is. So we can't calculate this without using a calculator. But on your calculator, you can type in the natural log of 19 and get an approximate answer of 2.944. So we talked about exponential functions and logarithmic functions being inverse functions, or that they undo each other. And how this works, we're just going to do a couple examples of this, is if you have a log with a base that matches the base of an exponential, those two things cancel each other out. And we're just left with our answer of x. Similarly, if you have a base that's being raised to a power that has a log with the same base, those cancel each other out and we're just left with x. So here's a better example with some actual numbers. We have a base 10 to the power of log base 10. Remember, if there's no base there, there's an invisible 10 of 4. Well, because these are inverses of each other, this base 10 cancels out with the log base 10, and so our answer would just be 4. But on this next example, the base on the log does not match the other base. So what we can do is we can rewrite that 25. 25 is the same thing as 5 squared. And don't forget this x. We can rewrite 25 as 5 squared, and now the base of the log matches this base that's being raised to an exponent. So these cancel each other out, and our answer is 2x. So logs and exponential functions undo each other. When we are finding the inverse of any equation, remember your first step is to flip-flop the x and the y. So this would say x equals 5 to the power of y. After we flip-flop the x and the y, our goal is to get y by itself. Well, we haven't really learned how to get y by itself yet. So what I would do at this step is I'm going to rewrite this. Right now it's written as an exponential function. I'm going to rewrite it as a log function instead. So as a log function, that's what we practiced in the very beginning. My base is 5. Log base 5 of x equals the exponent y. And hey, y is by itself. So this is the inverse function of y equals 5 to the power of x. In the next example, first step of finding inverse is to flip-flop the x and the y. This time, in an attempt to get y by itself, I actually can get rid of that 4 by adding 4 to both sides first. But then I get stuck. We haven't learned how to get rid of a base of 3 yet. So instead, I'm going to rewrite this as a log. Whenever I get stuck, I'm going to rewrite it in the other form. So log base 3 of x plus 4 equals the exponent y. And hey, y is by itself, so this is the inverse function. And I could write this like as an actual inverse. So if f was 5 to the power of x, the inverse of f is log base 5 of x, if I was being real official. But right now I'm just trying to isolate the y. So one more example of finding the inverse of an exponential equation. We're going to flip-flop the x and the y. And then we're going to try to isolate the y. Well, right now I can't isolate the y. I'm kind of stuck already. I have to get rid of the e next, and we don't know how to do that. So let's write this as a log. Log base e of x equals y plus 3. And I'm actually going to rewrite this again. Log base e is the same thing as saying ln. So ln of x equals y plus 3. The y is still not isolated, so my last step is to subtract the 3. Once my y is isolated, that is the inverse function. Let's do that same thing, but we're going to find the inverse of these log functions. So similarly, our first step is to flip-flop the x and the y. That's always your first step of finding inverse functions. And then we're going to isolate the y. Well, here we're stuck. We haven't learned how to get rid of a log yet. So whenever you get stuck, rewrite this in exponential form instead. Our base is 4. 4 to the power of x equals y. And now y is isolated, so this is the inverse function of log base 4 of x. One last example. Flip-flop the x and the y, and then we're going to isolate the y. Well, the first thing we need to get rid of is that ln, and we haven't learned how to do that yet. So let's rewrite this in exponential form. The base, when the log is ln, the base is e. E to the power of x equals y minus 2. And then to isolate the y the rest of the way, we're going to add 2 to both sides. And this is my inverse function.